Welcome back to the 23rd quarter of the complex numbers. We have started discussion on complex numbers and here we are on the 23rd lecture. In the 23rd lecture, which will be probably the last lecture of this series, we are going to deal with the residue theorem. In this video lecture of the residue theorem, we are going to understand the residue theorem, the motivation from Laurent series. We are going to reach to the residue theorem. We shall deal with the residue examples, then we shall state the residue theorem and we'll try to understand what it means. It's a very powerful theorem. The residue at removable singularities we'll try to learn. Then we'll try to learn residue for simple pole, and then we'll deal with some examples. Then we'll deal with double poles for residue and their examples. Then we'll deal with the residues at poles of order n. We shall end our discussion with evaluating integrals from the residue theorem. This is the most powerful technique that we are going to learn, which is at the end of this quarter. Probably this may cause little longer length of this video. The motivation for residue theorem is from Laurent series. Now let us recall the Laurent series. Let us suppose that f is a function that has an isolated singularity at z0. Some point we are considering where the function has isolated singularity. Let us suppose that this is the point z0 where we have singularity. Now, if the function is analytic in the region 0 less than mod of z minus z0 less than r. So here we are talking about a region of radius r, rather a region of radius less than r. So we are talking about this disk and the exceptional point is this z0. And what is the radius of the circle? The radius of the circle is r. And we are considering all those z which are lying inside the circle of radius r, such that z minus z0, that is the distance between 2 points mod we are considering. So z minus z0, this quantity is between 0 and r, and that describes a punctured disk. Why I'm saying punctured disk? Because there exists an isolated singularity at z0. And definitely this is very meaningful if and only if we are considering r greater than 0. If we shrink to r equal to 0, then the whole discussion is meaningless. In such a situation, function f has Laurent series expansion, and this expansion can be given as f of z. We have done this in the earlier lecture number 22. So this is equal to coefficients ak times z minus z0 to the power k, and the k factor is ruling from minus infinity to plus infinity. So this is valid for the punctured disk, which is described by 0 less than mod of z minus z0 less than r. Now here we are making extension to the situation such that we are interested in charting a new variable rho which is lying between 0 and r. So I would chart a circle of radius rho where rho is less than r. So here I'm talking about rho which is less than r and it's greater than 0. Under this situation, we can integrate this equation on both sides. And one more thing I want to narrate you at this point of time, that the series which is expressed here, I'm talking about this series. This series under this situation converges locally uniformly in the punctured disk. That's a key point. And because of that, we can interchange the summation sign and integration sign. Here we are performing integration over the disk of radius rho, and we have interchanged this sign and summation sign. So after doing that, we can write k is a constant and has nothing to do with the integration, so it is outside the integration sign. So we have summation k rolling from minus infinity to plus infinity ak into integration z minus z0 to the power k dz, where we are having integration that rolls around a closed contour of radius rho. On left hand side also the same thing, but for the function f of c. Now the immediate question is that what is the value of this integration? If you can calculate value of this integration, you can straightly plug in it here and we can find integration by this method for the function f of z by exploring the Laurent series expansion. This is true provided that the series converges locally uniformly in the punctured disk, on the basis of which we have interchanged the integration sign and summation sign. That's a key point. From the previous slide, we have borrowed this question. What is the value of this integration z minus z0 to the power k dz when the integration rolls over a circle of radius rho, which is punctured at z0? I mean to say that it has isolated singularity at z0. Now, this is a very routine integration that we are talking about, and this is equal to z minus z0 to the power k plus 1 upon k plus 1. So this to the power k plus 1 upon k plus 1. Now, in complex numbers, we do not prefer this language of speaking. And here I want to immediately mention that if k is equal to minus 1, so minus 1 plus 1 will be 0 and this function will blow. I mean the value of integration will blow. So here we are having a rider that k is not equal to 1. That is the condition. Then the function, so this function I am calling h of z, small h function of z equal to z minus z0 to the power k. It has a primitive. It has a primitive, and that primitive is named as capital H of z, which is equal to z to the z minus z0 to the power k upon k plus 1. So this quantity I'm talking about. So here instead of a routine language, we shall say that it has a primitive, namely capital H of z. Therefore, integration z minus z0 to the power k dz, which is rolling over a disk of radius rho, this is equal to 0 for k not equal to 0, for all values except k equal to. Now we shall discuss the most interesting case in this example, that when k is equal to minus 1. So k equal to not equal to -1 for all values of k except -1, this integration has zero value. You mind this. This is very, very important. This is very, very important. And then second important thing that we are going to do, when k is equal to -1, then this integration becomes integration 1 upon z minus z0 dz. We have plugged in k equal to -1, so this function blows at z equal to z0, and to solve this integration we are going to use the Cauchy integral formula, and we have done this somewhere in the earlier lectures. I would like students to go back to that video and understand Cauchy integral formula and the parameterization concept that we have done. So to keep this lecture compact, I cannot repeat those concepts here, and we have to find the this integration by using Cauchy integral formula, and the Cauchy integral formula for this situation is equal to 2 pi I, and this is for the value -1 because we have plugged in that value. Now our integration, which we were dealing since the beginning of this topic, integration f of z dz, integration or punctured disk of radius rho, is equal to summation k rolling from -infinity to +infinity ak into integration z minus z0 mod equal to rho into z minus z0 to the power k dz. This is equal to 2 pi I, as I said, and then this ak for k equal to -1. I'm talking about this ak for k equal to -1 is a minus 1. That is, we are talking about the coefficient of the term a minus 1, which has a factor z minus z0 in the denominator. This is the only value for which we have integration value, that is here. For earlier terms and later terms, we have this value 0. So all the way what we have to find is this ak, and this is why we have handled so many problems in the earlier video regarding finding a minus 1, and we can then integrate this function provided we can find ak. This is a very powerful thing, I believe. So friends, here we are in position to define the residue, and here goes the definition. If f is an isolated singularity at z0 with Laurent series expansion as f of z equal to ak into z minus z0 to the power k, where k rolls from -infinity to +infinity, mod of z minus z0 is allowed to roll between 0 and r, then the residue of the function, we are talking about the residue of a function at z0, which is in fact isolated singularity, is ak. So here we prefer to write res, that is the residue of function f at z0 is ak. That's the way. Now let us roll through an example, and the example I am considering is routine that we are considering in previous lecture. F of z is equal to 1 upon z minus 1 into z minus 2. So this function we have handled many times, and we have done a smart way of representing this and then writing the Laurent series without negative terms of k. So k is rolling from 0 to infinity. So that makes the story very simple. and for the previous part we have minus 1 upon z minus 1. So here we are talking about this series which is minus 1 into z minus 1 to the power k, where z minus z0, in this case it is mod of z minus 1, which is rolling between 0 and 1. Now here we shall have a diagrammatic representation for the same thing. We shall consider this as a real axis, this one as imaginary axis, this is the point 1, and this is the point 2, and we have isolated singularity at 1 and 2 for this function. Now here we are considering a circle of radius 1 centered around 1. So here I am talking about this very circle. And the isolated singularity is at this point. And here we have integration of this term vanishing. Rather, we are not bothered about anything. We are bothered about the coefficient by definition a minus 1. So we are bothered about this a minus 1. And here you can clearly identify that minus 1 is the value of this coefficient. So residue of f at 1 is minus 1. That's it. Now in the second example, we are considering the same function f of c, which has discontinuity at 1 and 2, can be written in a smart way as 1 upon c minus 2. This we have done in the earlier video, minus summation n rolling from 0 to infinity, this term. And here we are talking about the region of radius 1, a disk of radius 1 centered around minus 2. Now I shall draw a real axis and then imaginary axis. This is 1, this is 2, these are the two singularity points, and I'm interested in a circle of radius 1 centered around minus 2, sorry, plus 2. So here I'm talking about this circle. Now I'm not considering the point 1 because it is less than 1, not equal to 1. So here this circle has to be from inside 1. Now when we express it like this, the a minus 1 coefficient, which defines the residue, is coefficient of z minus z0. So this is the term z minus z0, and its coefficient is 1. So residue of the function at 2 is 1. Here I very quickly want to roll through some examples that we have already discussed, but now we are trying to find residue of those functions. Function is sine of z upon z to the power 4. This can be written by this kind of Laurent series, and in the entire series, which rolls from 0 to infinity, excluding 0 and excluding infinity, we have to consider the term where it has singularity. So this is the place where it has singularity, and this singularity is pertaining to the first term of ak coefficient, and therefore the ak coefficient is minus 1 upon 3 factorial. So this is the parameter a minus 1, ak where k is equal to minus 1. So that is minus 1 upon 3 factorial. It turns out to be minus 1 by 6. So the residue of the function at z equal to 0, function is blowing at z equal to 0. we have a disk of infinite radius and has a isolated singularity at origin. In the similar fashion, I will quickly go through when function f is cos of 1 by z. This has this Laurent series expansion, and here we have to identify the coefficient of 1 by z, and 1 by z is not appearing here because for 1 by z the coefficient is a minus 1, and 1 by z has disappeared because this coefficient is 0, so the residue is 0 for the function at 0. Similarly, when f of z is equal to sine of 1 upon z, we have this kind of expression, and again the coefficient of 1 upon z term is unity, so residue is equal to 1 for the function at 0. In the similar fashion, we have discussed this problem quite at length in the earlier video. F of z is equal to cos of z minus 1 divided by z square, and here you can make out that the term corresponding to 1 upon z, I'm interested in 1 upon z, and the coefficient of that is a minus 1, and that is disappearing in this series. Therefore, the coefficient must be 0. So residue of f at 0 is 0. We shall roll through some more examples. F of z is equal to 1 over z square plus 1. So in a smart way, we can write this as 1 upon z minus I into z plus I. So this can be further modified to express the series, to express this term like this. And here we have taken 2i common, and then you can isolate the first part with common denominator like this, and the second term that you can identify for the same denominator with minus z minus I upon the numerator. Now here we have this interesting term which has a minus 1, ak for k equal to minus 1, and the coefficient of that term is 1 upon 2i. So this can be further simplified as minus I upon 2. In the similar way, we can deal with the expression to find residue at minus I. So here we have found residue at I by substituting z equal to I, that is a singularity point, and here we are trying to find residue of the function at z equal to minus I, that turns out to be eventually I by 2. Let us suppose that here we are going to discuss the residue theorem, and this lecture is all about the residue theorem, and this is a very powerful theorem which is going to offer us integration in terms of ak coefficients. Now let us suppose that D is a simply connected domain, and this simply connected domain bears a function f, and this function is analytic in this domain, except for the isolated singularities at few points. These few points we are defining as z1, z2, z3, and so on. So here we are talking about some region D which is simply connected domain, and we consider function f to be analytic in this domain except for the isolated singularities. So this little cross, they are indicating isolated singularities. Then for C be a completely closed curve in D, orientate counterclockwise, and Z1, Z2 are the isolated singularities that lie inside C, and C is not intersecting the singularity. So we are talking about some region which is a closed contour indicated by C. Then integration f of z dz over the contour C, this is equal to 2 pi I times summation of all residues at singularities. Like here we have two singularities, so we have to consider sum of two residues. Likewise, we have seen earlier this kind of statement. This is not new, but here we have an extension that we are considering summation of all residues for those singularities which are encompassed into the curve which is a closed contour. Now here is the problem that we are going to discuss, and the problem is same because we have already solved it and we want to learn the next concepts. F of z is equal to 1 over z square plus 1. This has isolated singularities at plus minus I. So here you can watch plus I and this one is minus I. Now this function is analytic in the entire domain, which is the entire complex plane, except for the isolated singularities at plus minus I. And the annulus is different in different cases. Now, in the first case, I shall talk about the annulus C1, and C1 annulus I shall try to fill with some color, and except that isolated singularity at plus I, we have everything, every point within the contour C1, within the annulus C1, obeying the function to be analytic, except for the point plus I. Now, by our residue theorem, integration f of z dz over C1, this is equal to 2 pi I times residue of the same function at point I. And we have already calculated in one of the earlier slides that it is minus I by 2. So here you can clearly watch that this 2 is cancelled with this, and I into I will be I square, that is minus 1. Minus 1 into this minus will be plus, so we are left with pi. Now let us consider the annulus C2 and the region inside the annulus I'm trying to highlight for you. And here in this annulus we have isolated singularity by definition at minus I. In earlier example, we have calculated this point minus I for this function 1 upon z square plus 1. Now here f of z dz integration over C2, this is equal to, by the Cauchy integral formula, 2 pi I, residue theorem. We have used Cauchy integral formula to write this residue theorem, and this is 2 pi I times residue of the function f at minus I. And in the last example we have seen that the residue is I by 2, and here again the issue of cancellation crops in. This 2 will be cancelled here, and this I into I will be minus 1, so I square pi will be minus pi. Now for C3 annulus, we are trying to chart the area, and this area is the entire area enclosed by C3. So this includes C1 and C2 obviously, and here you can consider this complete area, and the most important point here to be understood is it contains isolated singularity at plus I and minus I. So these are the isolated singularities provided, and we have to calculate residue of the function at I and residue of the function at minus I. We have already done that, and by our residue theorem we have integration f of z dz over c3. This is equal to 2 pi I times sum of all residues inside the annulus. So here 2 pi I inside bracket minus I by 2 plus I by 2. So this amounts to 0. Now for your understanding, we shall consider a different annulus. Let us say C4, and this C4 is apart from the isolated singularities, and obviously the residue of the function inside out of the isolated singularities will be 0. Therefore f of z dz or contour ct c4, which does not include any singularity, this integration will amount to 0. Now I just want to quickly review what we have learned. So let us recall what we have learned. Let us suppose that f is a function that has an isolated singularity at some point z0, and if the function is analytic in the punctured disk, it means that function is analytic everywhere except z0, then we have mod of z minus z0 having any radius between 0 to r, not 0 and not r. So that is 0 less than mod of z minus z0 less than r. Moreover, this series that we are going to write for the function, which is a Laurent series expressed as f of z is equal to summation ak z minus z0 to the power k, where k rolls from minus infinity to plus infinity, has unique representation, and the series converges locally uniformly in this punctured disk. Then the residue of f at z0 is a minus 1. This a minus 1, I would like to further highlight that a minus 1 coefficient is associated with the term z minus z0 in this way. So in the Laurent series, this is the term of our importance. And here, the moment you find this coefficient, this very coefficient, the moment you find this coefficient a minus 1, it becomes residue of the function at z0. It is the coefficient of the term 1 upon z minus z0. I have written it already here. Now we shall deal with the residue at removable singularities. So the given function that we are considering f of z can be expressed as the Laurent series ak into z minus z0 to the power k, where k rolls from minus infinity to plus infinity. And here we consider that mod of z minus z0 is lying between 0 and r. So z0 is the point of isolated singularity, and Now we are going to talk about removable singularities. Now let us recall the old concepts. Z0 is a removable singularity. So when the singularity is removable, then the condition is that AK is equal to 0 for all k which are less than 0. It means that we don't have negative terms prevailing. What does it mean? It means that you can write this from 0 to infinity. So if so is the situation, then in particular AK for negative values it is vanishing. So obviously all negative coefficients are 0. Therefore AK is also 0 in this case, and therefore it is very obvious that the residue of the function f at z0 is equal to 0. Now let us roll through an example that will have more clarification on this concept. F of z is equal to sine of z upon z, and this we have already solved, and now at this point I'm not interested in repeating that which I have done some videos ago. Now this can be expressed in the series form as z inside the bracket z minus 1 by 3 factorial z to the power 3 plus 1 by 5 factorial z to the power 5 minus 1 by 7 factorial z to the power 7, and so on. So when we expand this bracket, what happens? So we are left with 1 minus 1 by 3 factorial z to the power 2, and so on. So here there is no term associated with 1 upon z. So the coefficient of this term, which we can call a minus 1, this is amounting to 0. Therefore, the residue of the function at 0 is 0. Now friends, we shall try and understand the residue at simple poles. So for the given conditions, I'm not repeating it every now and then, f of z can be expressed as a Laurent series ak into z minus z0 to the power k, where k rolls from minus infinity to plus infinity, and the series converges locally uniformly in the punctured disk of radius r, and this radius r has a relationship like 0 less than or equal to mod of z minus z0 less than r. So we are considering a disk of radius r less than r centered around z0. Now let us recall what is the simple pole. If the function has simple pole at z0, then if the series has a simple pole, then ak is not equal to 0. This is a very interesting thing because residue is this thing. Residue is ak, and this time ak is not 0, but ak is 0 for all negative terms smaller than minus 1. So how does that series looks like? So the series looks like this. A minus 1 upon z minus z0 is the only negative term present in the simple poles. And here we have great interest in finding this. This is non-zero this time, and the residue exists. Now, how to isolate this AK? That's a question. How to isolate this? This has gone clumsy. The idea is very, very simple. What we can do, we can multiply this equation on both sides by z minus z0, so that this z minus z0 will be cancelled and we can work out a minus 1. So to f of z we are multiplying by z minus z0. Here after multiplication we are left with only minus 1. Then a0 was not having any term associated, but here we have z minus z0 in multiplication, and one power is getting advanced. Here it is 1, here it is 2, and so on. So that's the only variation. Now how to find this a minus 1? So here residue of the function at z0 is a minus 1, and we can find a minus 1 under the limiting condition z is approaching z0. When z is approaching z0, what happens? This becomes 0. This becomes 0. All later terms, they are vanishing. So when we consider limit of this quantity z minus z0 f of z, then we are having only non-zero term ak. So here limit z approaching z0, z minus z0 times f of z will offer us residue, which is in fact a minus 1. Now we shall find residue at a simple pole through an example. Now here the example is we have to find residue of f at z0, which is a minus 1, and that we have developed a theory, a small theory, limit z approaching z0, z minus z0 times f of z will offer the required thing. So example, I am again repeating, f of z is equal to 1 upon z square plus 1. This has a simple pole at z0 is equal to I, and another one is at minus I. Let's not bother that. So residue of the function 1 upon z square plus 1 at I, this can be limit z approaching to I, z minus I times 1 upon z square minus z square plus 1. So we have to make some adjustments and solve this limit. So here we can write z square plus 1 as z minus I into z plus I, and here you can take liberty to cancel out this z minus I in the numerator and the 1 at denominator. Then without bothering anything, now you can plug in value of z as I. So 1 upon I plus I will be 1 upon 2I, that we can write as minus I upon 2, which is I think we have solved in one of the earlier examples. Now we are in position to understand how to find residue at double pole. For this, we shall consider f of z as a Laurent series ak into z minus z0 to the power k, where k rolls from minus infinity to plus infinity, and this is valid for all z mod of z minus z0 lying between 0 and r, but not strictly r and not strictly 0. We are not using equal to along with the less than. So this series converges locally uniformly in the punctured disk of radius r, which is centered around z0. Now let us recall the concept of double pole. Z0 has a double pole if a minus 2 coefficient is non-zero and ak is 0 for all k less than 0, for all k less than minus 3. So this is the negative term present. Beyond that, we are not having any non-zero term. Now, the expansion of this series f of z is equal to a minus 2 is the only valid negative highest term which is coefficient of 1 upon z minus z0 to the power 2. Then a minus 1 is prevailing, then a0 is prevailing, and all higher order terms are, positive powers are present, positive powers of z minus z0. Now, beyond this, below this, no term is present. Now, we have to isolate a minus 1. How to do that? So, to isolate a minus 1, this time we shall multiply both sides by z minus z0 to the power 2. So, z minus z0 to the power 2 into f of z, this is equal to a minus 2 plus a minus 1 into z minus z0 plus a0 into z to the power z minus z0 to the power 2 and so on. Now here we have to isolate the term a minus 1. How will we do that? Just pause the video and think what we can do. So here is the idea. If you differentiate this equation on both sides, what will happen? We have d dz of z minus z0 to the power 2 into f of z. This a minus 2 will disappear because derivative of the constant is 0, and derivative of this term a minus 1 into z minus z0 will be simply a minus 1. So 2 times a0 into z minus z0 and so on. Now here we can impose limit when z is approaching z0. What will happen? This will vanish. Along with this, all higher order terms will vanish. They will have 0 value for z approaching z0. So residue of f at z0 is a minus 1, and that is limit z approaching z0, derivative with respect to z of z minus z0 square upon into f of c. So that's the idea. Now we are in position to discuss example for residue at double poles. And what we have learned in the earlier slide is that residue of f at z0 is a minus 1 coefficient, which can be simply obtained by taking limit under z minus z0, z approaching z0 of d dz, that is derivative of z minus z0 square into f of z. If you do that, you can find a minus 1, which is happening to be the residue of the function. Now let us deal with the example which we have already handled in one of the earlier videos. F of c is equal to 1 upon z minus 1 whole square into z minus 3. So this function has double pole at z0 equal to 1 and has a simple single pole at z equal to 3. Now, by our theory which we have developed in the earlier slide, residue of the function, I have written function directly here, at z0 I have selected to be 1 because it has double pole at z0 equal to 1, and we are interested in finding residue at double pole. So this is equal to limit z approaching 1 d dz of this function. So here you can very clearly see that we can cancel out z square, z minus 1 square in the numerator and in the denominator, and we are left with 1 upon z minus 3. We have to find derivative of that, then we have to find the limit. So derivative will be minus 1 divided by z minus 3 whole square. So when we substitute z equal to 1, 1 minus 3 will be minus 2 square will be 4. So minus 1 upon 4. This becomes residue. Now friends, we can extend the idea of finding residue at pole of order n. We have seen it for n equal to 1, n equal to 2, and we can extend it for a number n. F of z is a function that can be expressed as a Laurent series ak into z minus z0 to the power k, where k rolls from minus infinity to plus infinity, and the series converges locally uniformly in this punctured disk of radius r, where z minus z0 mod is lying between 0 and r, strictly not equal to 0, not equal to r. So we are considering a punctured disk, means we are considering a disk at z0 of radius r, and we are considering annulus less than r and other than 0. Now the function z0, the function f, is a pole of order n if a minus n is not equal to 0. Below that n it is 0, and all ak's are vanishing. For all k, that is what I have said, for all k less than or equal to minus n plus 1. So how does that series looks like? The series looks like this. F of z is equal to a minus n into a minus n upon z minus z0 to the power n. So here we are increasing the order of n. So here we reach to a minus 1, which is a point of r importance, upon z minus z0. Then a0 having no power of z minus z0, that is power 0, and so on, higher order terms. Now the residue of, I'm generalizing the expression, residue of f at z0 is equal to a minus 1 coefficient, which is equal to 1 upon n minus 1 factorial times limit z approaching z0, n minus 1th order of derivative of the function z minus z0 to the power n into f of c. So here we have generalized what we have learned. Here we are at a very interesting remark on residues. If f of z is a quotient of two functions, g of z upon h of z, where g and h, they are independently analytic near z0, and h has a simple 0 at z0, then this is a very important condition. Then the residue of the function f of z at z0 can be expressed as g of z0 upon h dash of z0. Here the dash means derivative of h. Let us roll through an example that we have just now discussed. F of z is equal to 1 upon z minus 1 whole square into z minus 3. It has double pole at 1 and single pole at 3. So here we'll prefer to choose z of z as 1 upon z square minus 1, z minus 1 whole square, and h of z as z minus 3. So here g and h are analytic near z0, which is equal to 3. We are talking it is near to z0 equal to 3, and h has a simple 0 at z0 equal to 3. So here this function will vanish at z equal to 3. Now the residue of f at z0 is expressed as g of 3 upon h dash of 3. So here you very well can calculate g of z. So here g of z at 3, you have to replace this z by 3. 3 minus 1 will be 2, and square of that you have to find. So here I have written here 1 upon inside bracket 3 minus 1 whole square. Then h dash, derivative of this quantity will be 1. Derivative of z with respect to z will be 1. Derivative of 3 will be 0. And this thing divided by 1. So this is simply 1 by 4. Now we are going to learn the integral and residue theorem. We are talking about evaluation of integrals from residue theorem. Now let us suppose that D is a simply connected domain and f be an analytic function in D, except for the isolated singularities. Now, if C is simple closed curve in D, which is oriented counterclockwise with no singularities of f on C, it should not be on C, and let Z1, Z2, Z3 and so on up to Zn be those isolated singularities of the function that lie inside C, not on the C. Then integration over C, f of z dz, this is equal to 2 pi I into summation of all residues of the function which are inside the annulus we have considered as C, and these annulus are accounted for k rolling from 0 to n, whatever may be the number. Now let us deal with a couple of examples and we'll end this video lecture. So e to the power 3 by c, integration we are performing on mod of z equal to 1. In one of the earlier lectures we have done this kind of examples where we have worked out integration around a closed contour in the form mod of z equal to 1. So this is equal to 2 pi I times residue of f at 0. So here we are talking about all that punctured disk having puncture at origin and so on. So f of z we have equal to e to the power 3 by z, and that can be expressed in the form of series, which is 1 upon k factorial 3 upon z whole to the power k, where k rolls from 0 to infinity. Now the residue of the function f at 0 is equal to 3, and therefore we have to substitute the value of this and then we can calculate the integration. So we are going to use the residue theorem for evaluating the integrals. Here are some more examples for better understanding. We are integrating tan of z dz over the contour mod of z equal to 2. So this is equal to 2 pi I times sum of all residues inside the annulus, and the function f is tan of z, which can be written as sine z upon cos z. Now find the residue of the function at pi by 2. We can employ the earlier remark that it can be expressed as a ratio of two functions. F of z is the quotient of g upon h. So here we have identified that form. So g of z is equal to sine of theta and h of z is equal to cos of theta, and it is analytic near pi by 2, and h of pi by 2 is equal to 0. All the conditions for that remark, they are satisfied, and we can find residue of f at pi by 2 equal to g of pi by 2 and h dash, that is divided by h dash of pi by 2. So here we can work out sine of pi by 2 upon minus sine of pi by 2 equal to minus 1. In the similar fashion, we can find residue of the function at minus pi by 2, which turns out to be again minus 1. Then the integration tan of z dz over the contour or annulus mod of z equal to 2. This is equal to 2 pi I times sum of all the residues inside the annulus. So that is minus 1 minus 1. So minus 2. So in all it becomes minus 4 pi I. Let us roll through one more example wherein we have contour C1, which is red line appearing on the screen, which I am trying to highlight for you. So this is the annulus C1 and the function is having double pole at 1 and single pole at 3. This is to be integrated with respect to z. This is equal to 2 pi I times residue of the function at 1. So here this is 1. So we are trying to find residue of the function at 1 and the annulus is C1. So obviously it can be found by limit, one of the earlier methods we have learned just now, z approaching 1 d z of z minus 1 whole square upon the function parameters, that is z minus 1 whole square into z minus 3. So here you can simply identify that you can eliminate these two terms which are appearing in the numerator and denominator. So that leads us to a simplification that we have to find d dz of 1 upon z minus 3. So the derivative is minus 1 upon function to the power 2. And then we have to sublime the limit z equal to 1. So 1 minus 3 will be minus 2 square will be 4, and in the numerator we have minus 1. Similarly, so integration over C1 function dz, that is equal to minus 1 by 4 is the residue that is multiplied by 2 pi I. So in all it becomes minus pi I upon 2. Similarly, we can find the annulus C2, which I am trying to highlight again for you as the blue line in the counterclockwise direction. So this is the annulus C2. Now it encloses two singularities 1 and 3. So the function remaining the same, we have to integrate over C2 dz. It is 2 pi I times sum of all annulus inside the annulus, sum of all residues inside the annulus, so this is equal to 2 pi I times minus 1 by 4 plus 1 by 4. So we have to find it at two places, 1 and 3. Here I have clearly indicated you the solution for C1. This annulus is minus 1 by 4. In case of this, the annulus is plus 1 by 4. So in all, it becomes 0. So residue of f at 3, here is the simple calculation you can see. Thus here we have concluded evaluation of integrals from residue theorem. This was a little lengthy, but in turn very simple. You have to get involved, and you cannot isolatedly come on lecture number 23 and learn. You have to smoothly go through. Moreover, I would like to advise students to learn this subject in all the sequence the video lectures are presented. Moreover, I would advise you to learn it in compact time so that you don't forget earlier concepts. So thank you very much for your patient listening, and I'm very delighted in delivering these lectures. Thank you so much.